All right, today we are doing a lesson with the objective to recognize imaginary numbers and apply the concept to zeros of polynomials. Now, imaginary numbers is something that we could really deep dive if we wanted to. You should hit this in your later math courses, especially like a pre-calc. Later on, we are going to cover the surface of it, mainly to help us apply the concept of this to polynomials. So, before we get into our note sheet and all of these examples and everything, I want to kind of back up and just this is how we set up our notes in class. So we said what numbers can we square in order to achieve the following. If we look at 4, okay, we could have gone 2 to the second power, which is 2 times 2 equals 4. We could have also done that with negative 2. Negative 2 to the second power is negative 2 times negative 2. That equals a positive 4. So for part B here, we could have done it with 5 squared or negative 5 squared similarly, right? There's a positive and there's a negative. And for part C here, we could have done positive 8 squared or negative 8 squared. However, as soon as we get to problem D, where we're trying to target a negative number, there's nothing that we can square to get a negative 64, right? Because if I do positive 8 times positive 8, that's a positive 64. Negative 8 times negative 8 is positive 64. We can do that mismatch of 8 times negative 8 to get negative 64, but that doesn't really square the number, right? So mathematicians created this idea of an imaginary number to help us accommodate that. And this is where we're going to kind of go into our notes here. So a couple of definitions to get down. First is imaginary numbers. Basically, when squared, these are going to give negative results. If you notice, the imaginary number I here is defined as I squared equals negative 1, and I equals the square root of negative 1. So if you are, let's say, in a future math class and you're using this, you might get the instance of the square root of negative 64. Now, if we think of the square root of positive 64, that is just 8. But the square root of negative 64 is going to be 8i. We can't actually take that square root, and so we throw that imaginary number on top of it or along with it to kind of accommodate that and deal with it in math. So these will often show up as complex numbers where it's some combination of real and imaginary. Notice this example here. We have a normal 7 plus some imaginary number 3, and we can tell it's imaginary based on that I that's with it. That tells us it's imaginary. So complex numbers are always going to have a real component and an imaginary component. Before we apply this to our polynomials, let's just kind of examine what these complex numbers look like, really firm up our understanding. So for each of these examples, 1, 2, 3, and 4, there is a real component and there is an imaginary component. All right, so real equals something and imaginary equals something else. Okay, and actually, so if we look at our real component, those are going to be the numbers that don't have any I associated with it. So for example, 1, it's 1. But for our imaginary component, that is going to have the I associated with it. So in this case, it's a positive 2. If we move on, and I'll start color coding these. I should have done that in the first one. We'll have a real component in example 2, a real component in example 3, and a real component in example 4. Should be able to try and find all of those. And then we also have imaginary components in all 3 of those as well. So for example 2, the real component is 8. And that imaginary component is negative 3. Notice how I'm not including the I in there. I'm just including the size of the imaginary component. Then our real component in example 3 is negative 2 and a positive 4 for the imaginary component. Lastly, it should be easy to find the imaginary component for example 4. It's 6. And since there is no real component listed, it's kind of the same thing as saying 0 plus 6i. So that real component is 0 there. Now, this is a really quick view of what complex numbers look like. And it's most important to just be able to recognize what they are. When we see this I, we know there's an imaginary number involved. We know the number is then complex. We are going to apply this to our concept of polynomials to help us deal with some of the discrepancies we saw in class today. So, some keys for imaginary zeros, and you don't have to write these down. These are on your notes. First off, any polynomial of degree n has n zeros, roots, and solutions. So if we have a fifth degree, that means we should expect 5 zeros on our graph or in our polynomial. Okay? As we saw in class today, some of our zeros, roots, solutions are going to be visible, and those are going to be real. And we've been working with real zeros up to this point, while others are going to be imaginary. And honestly, today, it's enough to know that imaginary zeros exist. Then, the final topic, and this will lead into our first kind of examples, is that these imaginary zeros, roots, solutions, they always come in pairs. And the real component is going to stay the same, while the sign of the imaginary component changes. Let's see what I'm talking about here. So, if we have an imaginary zero at 1 plus 2i, that means we are going to also have an imaginary zero at 1 minus 2i. Notice how that real component, the blue component, stayed the same. The imaginary component flipped. Okay, if there's imaginary zero at 8 minus 3i, then that real component is going to stay the same. And we also have an imaginary zero at 8 plus 3i. Final example, if there's imaginary zero at negative 2 plus 4i, then there's also an imaginary zero at negative 2 minus 4i. Notice how in each of these examples, the real components stayed exactly the same. 1, 8, and negative 2. It was these signs in front of the imaginary components that switched. Okay, that's how these pairs of imaginary zeros are going to show up in our work. So, for each of these polynomial equations and their graphs, we are going to identify the number and types of zero presence. We're going to build, starting with example 8, kind of build the complexity in 9, 10, and 11. But basically, we're going to kind of do this by listing out what we know. So we know from the degree of our polynomial that there are going to be 3 total zeros. If we then look at our graph and look at our x-intercepts where our zeros are located, there's one there, there's a second one there, and there's 3 there. So there are 3 real zeros. I'm just kind of labeling these right here, right? We have 3 real zeros on our graph. That means that the number of imaginary zeros that we would have left over are 0, right? We have 3 total. 3 of them are real. So 3 minus 3 leaves us 0. We don't have any left over to be imaginary. Let's take a look at what having imaginary zeros looks like then. So in this example, we also have a degree of 3. So we are expecting to have 3 total zeros on our graph. However, if I look at this graph, I'll notice that I only crossed that x-intercept once, right? So I only have that one real 0 that we can see. In that case, then, I have 3 total. I only have 1 that I can see that's real. That means we have 2 that are imaginary, right? 3 minus 1 equals 2. 2 have to be imaginary there. Let's keep going with this. You should be able to start trying this on your own if you can. Example 10, we have 4 is our degree, so we should expect 4 total zeros. If I look at my graph, it looks like we have 1 here, 1 here. And so we have 2 real zeros on our graph, which that should tell me that 4 minus 2 leaves that we should have 2 imaginary zeros that show up. And lastly, example 11. This one's the trickiest one, all right? We have a degree of 4. So we should have 4 total zeros. Now, I have a 0 right here at my x-intercept. However, since this bounces back, it has a multiplicity, right? Multiplicity. And that means that it shows up twice. So even though I am hitting my graph once, hitting that x-intercept once, the amount of real zeros that we actually accounted for on that graph is 2, meaning that we have 2 imaginary zeros left over. And let's remember, if we had, let's say 4 minus the 1 real zero for that spot, we'd be left over with 3. But that can't work because those always come in pairs. Remember, imaginaries always come in pairs. So we also got to look out for that multiplicity when we're trying to find the number of zeros.